No, guys, can you hear Tom?
Yes.
Thank you very much. I'm fixing all the stuff. We start in 5 minutes or less. Okay, guys, it seems it takes more time today because it is the first time we are using this room. So I have to work a little bit more on, but we are going to start in a few minutes. Okay. program, okay. Okay, so, okay, registration. This morning I uploaded our last class. No, it was for the other class. Sorry. Yeah, sorry. Okay, it will be. I understand it is Friday, so it's Friday for me as well. So we'll take it slowly. Okay. So, new registration, what's happening here? So, microphone should be, okay, so microphone should be Jabra speak. And then we say this is class, so apply econometrics. Of Friday 11. So, okay, I think we can start. So, good afternoon, everybody. I can close this one. Before coming here, I sent you some material we're going to use today, but let me say that the path we are following, let me show you the program again. So this is what we are doing. Please let me know if at home you are not listening to me, if you can, because it's a very different room relative to the other rooms. Can you hear me at home, guys?
Yes, you can.
Okay, very well. Thank you very much, guys. So we are working on. We have to finish to say a few words about misspecification issues. Which is actually a very large topic, because it's very. We are just focusing on the very essential ingredients of, say, deciding whether a model is good or not. We know that there are many elements that contribute to the evaluation of the model, and then today I would like to start, but in an easy way, moving to. One thing I want to say that I skipped say confidence intervals, and not confidence interval, predictions, forecast. I want to come back on that at the end, the very last end, but not just because I am kind of schizophrenic, moving up and down, no, just because it is a topic that I can sacrifice, if needed, I can sacrifice it. So it's very important that I move to the instrumental variable estimator. Then, if we have time, we can come back to the prediction, which is it holds prediction regardless of whether we are doing OLS or instrumental variable. So it will be a very easygoing thing to understand. So today we were discussing in our last class we were discussing a test for testing the absence of correlation, serial correlation in the error model when we are dealing with a model based on time series data. Okay, and what we said in our last class is the following. I go to the slide. I want to come back on the concept because it is very important. I'll show you an example. I want to clarify one thing, because maybe you might be tempted to make a wrong conclusion. Let me clarify what I mean. So in our last class, we have been discussing, say, this is the example. I have been considering the following motivating example as an example where imagine that we have this model. We have a model we want to explain the it is our model for the log of real per capita gasoline consumption, okay? And the feature of this model, it is a dynamic linear regression model. When I use the word dynamic, I mean that, say, the endogenous variable enters among the regressor, but dated t-1, t-2, okay? And the example we have been discussing in our last class was the following. If the error term epsilon t is correlated over time, for instance, if epsilon t, for instance, has the following structure, like, say, that we call autoregressive model of order 1, I imagine that with Professor Panagionitis, you will be working quite more intensively on this class of models. But this is a model where the error to the time t is related to the error to a time t-1 plus, say, white noise unpredictable component there, okay? And the rho 1 is the coefficient which links, rho 1 must be between 1 and -1, okay? Is the coefficient which links, say, the error at time t-1 to the error at time t. And what we have been studying, what you find in this slide, let me see if you're looking at me. Okay, you can see me here. Maybe I better do like this. Okay. So the important thing is that in what we saw in our last class is that if the error term is like this, and if the model is like this, then we have correlation between the error term and the regressor dated, the endogenous variable dated t-1. And after the class, I had some conversation with some of you, and this is, and I realized that there is something I can clarify. Imagine that the model is such that we don't have this component here, okay? So we basically, the model is such that gasoline consumption only depends on the price of gasoline, on the income, and error term, okay? In this case, if the error term, again, is AR1, so it is autoregressive process of order 1, of course, in this case, we no longer have correlation between, we don't have, say, the endogenous legs of the endogenous variable. So the error term is still uncorrelated with price and income, okay? So what's the issue? The issue is that, do you remember the case, the very important thing when you do empirical analysis is think about, when you have your problem, think about the big sigma matrix. The big sigma matrix is the one which captures important information in your data, like, variance, homoscedasticity, heteroscedasticity, and correlation or absence of correlation. Now, a nice exercise that I would like you to consider, I will formalize it and send you, will be, imagine that you have, say, a model like this with the error term like this, where look that I'm giving you a lot of information. The slides say that in this model, it is possible to prove that the covariance between epsilon at time t, the error at time t, and the error at time t minus s, for s, 1, 2, blah, blah, is given by the power of rho 1. So, I'm giving you implicitly are the off-diagonal elements of the big sigma matrix, if you think about it. I'm telling you that the big sigma is not diagonal. One problem might be, okay, what about the diagonal elements of the big sigma matrix? The diagonal elements are the variance of epsilon t, okay? Is it difficult to derive the variance of epsilon t from this model? This is a very nice, I would say, beautiful exercise to do. an exercise where we find that we are, if you come back on the slides where we have the 4 cases about the big sigma matrix, this will be case number 3. That is, we have homoscedasticity, because if you take the variance of epsilon t from this model under some conditions, we can do that today. We realize the variance is, at the end of the day, is constant. So on the main diagonal of the big sigma, we have something which is constant. And the off-diagonal elements are given by these elements. So we are, it is what I'm giving you, it is a generalized linear regression model, because the big sigma matrix, first of all, is not diagonal. The elements on the main diagonal are the same, so we have homoscedasticity, but we have correlation by construction. So, optimal estimate. So we know that in cases like this, so we don't have correlation between the worst situation ever is when we have correlation between, say, some of the regressor and the error term. But imagine that we don't have this element. Okay, the selected one is not there. Okay, so. If we have a model like this without the selected regressor and epsilon t is autoregressive order 1 like this, then we have a situation where the big sigma is not diagonal, which means that the ideal estimator of beta is a GLS. Now, we said when we are in a situation, when we face a generalized linear regression model, there are 2 ways to go, where we know, of course, provided that we know that there is no correlation between regressors and the error term, otherwise our interpretation breaks down, okay, of the model. So we know that when we face a generalized linear regression model, there are 2 ways to go. One is to still stick to OLS. We know that OLS will not provide us with the best standard error, but what we can do, we can robustify the standard error. So we flag the option robust standard errors. The alternative is, you know, I presented you an example where we had the heteroscedasticity. If you think about that, you remember the Kuznets linear approximation example. In that case, what we did was modeling explicitly the heteroscedasticity. By what we did, we made an hypothesis where we connected the heteroscedasticity to observable variables. And we also showed that we did a good job at the end of the day, because we managed to control heteroscedasticity in that example. In this case, of course, there are ways to go. Also, if you want to get the best standard error for the OLS estimates of B1, B2, and B3, but we have to take into account for the information that there is some, we have to take into account the information provided by the big sigma matrix. And also in that case, it's possible to prove, if we had 60 hours rather than 30, I would have been discussing a very traditional way, which is another example of a feasible GLS model, which says, for instance, we try to estimate this row 1 from the data, and once we estimate this row 1 from the data, we have the big sigma. You have the element, you have a kind of estimate of the big sigma, so you can apply a feasible GLS estimator. Are you following me, guys? Are you understanding the main concept? That is very important. If you say, I don't have a clue what the hell this guy is telling us, it means that you have to go back to the slides and with very patient, you have to go back. Otherwise, if you're understanding, it's a good sign, okay? Good thing. Now, just I want to discuss with you very quickly, how do I compute the variance of epsilon t in this model? We can do the following logical exercise. Let's think about let's assume that this is a linear regression model. Actually, it is a linear regression model. The only difference is that we know that the error are not observable. Okay, but if epsilon t would be observable, this would be a very simple linear regression model. Okay. Now, if I take the variance of epsilon t on the left-hand side, okay, so it will be the variance of this guy, okay, and we know that when we have to compute the variance of the sum of two random variables, we have to do the variance of the first element of the sum plus the variance of the second element of the sum plus 2 times the covariance between the two elements, right, guys? So, let me call on the left-hand side the variance of epsilon t, call it sigma square epsilon, okay, on the left. So, let me call the variance of this term, like you understand it will be rho 1 square, because rho 1 will go outside variance with a square, because it's variance. And imagine that we have a condition that the econometrician calls stationarity. Stationarity, let's stay to the intuitive definition. Stationarity means a variable which fluctuates in a quite regular way around some constant value for it. So, if you are computing the variance of this element, you could say that, say, you have rho 1 squared times the variance of epsilon t minus 1, which is, if in a regularity condition, is the same as the variance of epsilon t. So I can solve the variance of the first element like rho 1 squared times sigma squared epsilon again, okay? So we have sigma squared epsilon equal to rho 1 sigma squared epsilon. Then I have the variance of v, which is sigma squared v. And then we have 2 times the covariance between this element and this element. What about this covariance? Do we know the value? Why you say no? You should say yes. It's a regression model. It's a regression model where the error term is uncorrelated, white noise. The regressor is homogeneous time t minus 1. Do we have correlation between this element and the other one?
Oh.
Sorry?
It's white noise.
This is white noise.
It's something that...
Yeah, we know. Right, good. We know that since Vt is white noise, so is uncorrelated over time, it will be no link with the past. So, coming back to my point, the variance on the left-hand side will be the variance of this term plus the variance of this term plus 0. Because there is, when you have the regressor is dated t minus 1, it will be uncorrelated with a white noise error term. So it's very easy to compute. You have an expression, you can write on your table now. You have sigma square epsilon on the left will be equal to rho 1 square sigma square epsilon plus sigma square v. You can solve and derive sigma square epsilon. And you get the element on the main diagonal, the big sigma method. The trick, the secret, is always thinking about, given your problem, think about the big sigma. That is the suggestion I give you. Because thinking about the big sigma gives you indication of the structure of your data. When you understand the structure of your data, you know which is the best way to go. Okay? So basically, what I'm telling you is that we know this, the variance of the error term, which will be constant under the stationarity condition. If the variance of epsilon t is the same as the variance of epsilon t minus 1, I'm imposing homoscedasticity. And I also know off diagonal term of the big sigma. So I have everything. I have everything.
Why the two big sigma square are the same for t minus 1?
Because I'm imposing the one condition. One condition is that this model, the rho 1 less than 1 in absolute value, means that we're dealing with a stationary models in time series. You will discuss that series with Professor Panagonidis, but let me just give you the intuition. A stationary model is a model where the expected value of the time series is constant, and also the variance is constant. So you have implicitly, you have almost skedasticity by construction. Okay? So this is, and now I have given you all the ingredients to write the big sigma in this example. Okay, so I wanted to, why I'm discussing, why did I come back on this? I come back on this just to recall you that in this example, in the slides, we have correlation between the error term, when the error term is not y naught, but it's given by this, okay, and Ct minus 1, because we have this lag. If you don't have this lag, basically, even if epsilon t is autocorrelated over time, we not necessarily have correlation, okay? And that was, anyway, regardless of whether we are in this case or we don't have this element, it is very important to test the absence of correlation in the error term. When we are dealing with time series data, when our regression model is based on time series data, one of the first concerns in our empirical evaluation to evaluate the empirical validity of a model will be testing the absence of serial correlation. The term is serial correlation over time, okay, of the error term. And we already know how to do that. We know, for instance, how to study the correlogram, autocorrelogram. Let me provide you, let me come back on our empirical example, okay, so that you can understand what I do. It is, you know, now it has become our leading example this year, the gasoline consumption. Okay, I fixed it in English. This is really, wow. Okay, no, okay, I have to close it. I imagine that I close it and then restart it again. Okay, I restart it again, and now it is in English. And then I increase the font scale. We typically use 15, right? Something. Sorry, 20. Okay, let's do 20. Okay, 20. And now we have been working quite a lot already on this model. Now I give you, after some, you know, many estimation, many analysis, blah, blah, which is what we do when we face the data, when we actually face the data. The model I'm going to estimate, it is a demand model for gasoline, and I want to come back on it because it will be our leading, one of the leading cases we investigate, also when we move to a new estimator, the instrumental variable estimator. But given our theory, now what I do, I want to model, say, the growth rate of gasoline consumption. I do that because you will see with Professor Panagonitis that the growth rate of gasoline consumption, this model will be a stationary variable, while the level of consumption, the level of gasoline is not. You can see from the graph. I'll show you now the graph very, very quickly. So I'm going to model the growth rate of gasoline. Since I have the log of per capita gasoline, I know that I take the first difference, that will be the growth rate, and we know that. And so the determinants will be the growth rate of income, of, say, total expenditure, and it will be the growth rate of the price of gasoline. Okay, this is my model. So it's the advantage in this formulation is that growth rate of gasoline time t constant, growth rate of total expenditure at time t, and the growth rate of price of gasoline at time t. Okay, I click OK. I don't click any robust standard error because I want to test. In order we are discussing about the misspecification analysis of the model. Okay, and so I click OK, and the first check I will do, because we know that. Okay, first of all, I see that the estimated coefficients are both strongly significant. Look at the t ratio and p-value. The theory I have in mind in this setup is when I have time series, guys, I remind typically large sample theory. Okay, I understand that 34 is not that large, but let's assume that it is fine. Okay. Now I see that the two estimated coefficients are, from the point of view of economic analysis, they are both strongly significant, and the sign is in line with our expectation. So it seems we have a good demand model for gasoline, or a potentially good, a candidate good model. Now we have to check that it is good or not. The R square that you like very much is not that bad, 77%. Just let's look at the graph, actual fit and the residual. No, the graph. I always miss a graph. Fit, actual plot against time. You can see that we already saw that our model, which is the red is the actual, the true value, and the blue is the one predicted fitted by our model. It's the appealing feature of our model is that we capture this peak more or less, and this peak, which is not quite good. We don't capture the Gulf War, Gulf War of 91. Iraq invaded Kuwait, and then it became war with the US and the West countries. But we do quite well here, and then we have Scott. This model looks pretty good. Okay? Yes?
What happened before the 70s?
During the 70s,
I'm not talking about the energy prices, but the model, see, the trend is the opposite.
Where? Here? Yeah. I don't know what we don't capture here. I don't know. I really don't know what is why we don't pick up this peak around the 60s. This could be also, I don't know actually. I have no idea about that. So that's why we should be an expert. There has been also some wars in
maybe
yes, exactly. I had in mind that, but maybe it could be this drop here of consumption. I don't know, but then there is this recovery. I actually don't know.
I was not referring to the historical part, but the model. You see the line, there is a peak of the actual line, and the fitted goes in the opposite direction.
You mean here? Yeah, but it happens. It happens. You would like not to happen. It's very difficult that you can model or say the entire sample This is, I would say, this is already quite good from my point of view. Okay, but now, we are quite okay about the fit. Okay, more or less. But now we have to to take some. The first thing I will check. I will test is whether we have homoscedasticity or not, because if we find that, if we reject the null of homoscedasticity, we know either we robustify the standard error, so I re-estimate the model by flagging robust standard error, or if I am a braveheart guy, I'm going to model the heteroscedasticity. Okay, but so what I do now, I test heteroscedasticity, Y test, we know the Y test, so I'm running the Y test. I just focus on what reported in the output. So the hypothesis is at homoscedasticity. You can see that we strongly accept at the 5% level the null hypothesis. So we don't have any, heteroscedasticity issue. So the big sigma metric has constant element on the main diagram. Okay. The second check, important check in this time series model estimate on time series data is what happened? Okay, is now the absence of correlation in the residuals, because we know residuals are kind of measured empirical measure the errors. We don't see the errors, but after estimation, we get the residuals. So what we know up to this point, we can do the following residual correlogram analysis. We already did it together. So I click residual correlogram, and we know that basically we find that I just look at the top panel. We see that those are the red lines, red bars, sorry, are the estimated correlation between the residual at time t and residual at time t-1, t-2, t-3, and we see that, I mean, the bars are inside the blue confident bands, and if we look at the Q test statistic, we realize, we looked at the P, we never reject the null hypothesis of no correlation, so it is quite good. But there is also, we left in our last class, next it was Tuesday, we left with the following test, which complements the autocorrelogram, okay? So under test, we were discussing the autocorrelation test, okay? So what I want to test is, in addition to the analysis of the residual autocorrelogram, I want to test the null hypothesis that there is no correlation in the error test. Okay? What I'll do now, I show you the test empirically on Gretel, and then we come back to the slide and we rationalize what Gretel has done for us. Okay? That will be my job today. Not only that, but okay. So autocorrelation, by default, Gretel says, okay, large order of the test is 1. Let me put just for the moment 2, okay? Then we'll understand the meaning of this later on. I click OK, and let me show you, say, the result of the test is written here. So again, the test recall that the null hypothesis, and this test is known as Breusch-Godfrey test, okay? The null hypothesis that the error term is not autocorrelated over time. So basically, the null hypothesis, if I would be like the error term, this one, so rho 1 is equal to 0. If rho 1 is equal to 0, you have that epsilon t is equal to Vt, where Vt is a white noise. So no correlation. Okay? So coming back to the test. So the test statistic is 1.07. You can see we see that the p-value of the test is quite larger than 5%. So we accept the null hypothesis of absence of correlation. And this version of Gretel provides me with also alternative test, but you know the outcome is exactly does not change. Okay, we don't reject the null. So the test, the Breusch-Godfrey test confirms the analysis of the autocorrelogram we have done together. Okay, so we have very nice elements that seem to support that our estimated model for the growth rate of gasoline consumption is satisfactory one. Okay, but now let me give a look to the upper panel of the test, and basically the test is built like this. But we are regressing the residuals of the OLS regression over, you can see, all the regressors of the model, constant growth rate of expenditure and growth rate of price of gasoline. And then I have one leg of the residual and a second leg of the residual. I asked Gretel to consider 2 legs, the option 2. Okay? If I had selected 1, I have just found 1. And what is this test about? The test is a joint test of significance of these 2 regressors, of residual t-1 and residual t-2. And that's why you find an F with 2 degrees of freedom, because we are jointly testing that 2 parameters, 2 coefficients, are jointly equal to 0. Okay? Just for robustness, let me run again this test, but I leave the option, sorry. This was the output. So it is nice that Gretel report this test in the main output. That is a nice thing. But let me rerun again the test by leaving 1, autocorrelation 1. You will see that now you will find only one, say, the residual t minus 1. And but again we do not, at the 5% level of significance, we do not reject the null of absence of autocorrelation. So I would be tempted to, let me show you, very quickly to show you one of the slides I sent you this morning. Oh, not this morning, before coming here. There should be a graph here. Yeah, so if this is, let me show you this graph. If you have in mind, if you are, say, an economist, you are estimating gasoline demand model for gasoline. So this is the price of gasoline, this is the quantity. Actually, we're working growth rates, but we are just in quantity. So we know from theory that a demand curve is something like this. So, and we have estimated, say, the coefficient beta 2 to be negative and strongly significant. And demand should also, the demanded quantity of this case gasoline depends on price and depends also on expenditure. We can interpret in this model the error term as a demand shock, if you think about it. And this will be important later on. But so we have estimated a downward slope demand equation, which is what we wanted. In particular, we wanted this coefficient here, this one, no, sorry. We wanted this coefficient here, this number to be negative. And let's keep in mind this number, minus 0.21. This is the elasticity of gasoline demand with respect to price. It's the elasticity of growth rate of gasoline demand on the growth rate of the price. Okay, and apparently this is a very good model. According to also even considering the R square, it's good. No heteroscedasticity, we have homoscedasticity, no autocorrelation. At the end of the day, I could use this model to make predictions, okay? But later on, we'll come back on this model because there is one thing we might, there's something that we might question about this model. But for the moment, I want to finish my job. My job is, I want to explain you what happens with the LM Breusch-Godfrey test for absence of autocorrelation. So I'm coming back to the slides, okay, guys? And after I show that, we make a break. So I think it was important coming back on this concept, but also because we are tired, we don't need to make any rush. It does not make sense. Okay, the LM test for autocorrelation, the Godfrey-Breusch test, okay? So imagine that the assumption, the underlying assumption is that the errors of the model are generated by a model like this. So the error time t depends rho 1, error time t minus 1 plus rho 2, error time t minus 2, blah, blah, rho tau, error time minus tau, plus Vt, where we know Vt is a white noise term with variance sigma square V. Okay? So what we want to test, the null hypothesis we have in mind, recall that when we test, recall the 3 ingredients of a test: null hypothesis and alternative, test statistic, and a decision rule. Those are the essential ingredients for running a test. If you have these 3 ingredients, you No way. Okay, but so the null hypothesis will be my null will be no correlation. So I want to kill row 1, I want to kill row 2, I want to kill row tau. So jointly, of course. So the null hypothesis is that under the null, epsilon t is equal to Vt, because we are killing this part here, the one I'm touching with my hand. Okay, guys? So under the null, epsilon t, the error term, is a white noise, and the white noise is uncorrelated over time by construction. Now the alternative, what will be the alternative? The alternative will be that at least one, row 1 or row 2 or row tau, one of these rows is different from 0 in the population. So under the alternative we have correlation. And so when we have correlation, and coming back to my starting point today was, okay, we have correlation. If we have, say, if in the model we have, I have the growth rate of consumption t-1, and I have correlation, I am in trouble because the OLS estimator will be no longer consistent. If I don't have one-leg regressor, I know that the OLS estimator is not the best one I can use. Okay? So the tests work like this. So it is very important checking the absence when you are you understand when you're dealing with cross-section data, we don't give absence of correlation as given, as granted. It is with time series that we check it. With cross-section data, we are only concerned with the homoscedasticity or heteroscedasticity. With time series, we are concerned with both things. Okay. Now, what Gretel does is the following. Imagine that Gretel estimates the model by OLS, and by doing that, one gets the residuals, okay? So epsilon t up. We know that after estimation, we have beta up, and so we also have epsilon up, residuals. Then, you know, the upper part of the output of the Gretel output, we have the result of an auxiliary regression, where, say, on the left-hand side, I have the residual. Let me show you. I'm not telling you lies, because the test was this one. No, sorry, this is the heteroscedasticity. Let me come back on. Not this, let me also this. Not taking the right thing. Okay, this one. I'm regressing the residual over what? Coming back on the slides. I'm regressing the residual all the regressors of the original model, plus residual t-1, residual t-2, residual t-ti with coefficient row 1, row 2, row tau, and so on. And the test reported at the bottom, so this regression, those are the original regression of the model, and then since I selected just one leg in the option Gretel gave me, I'm regressing the residual on the residual t-1, and the test is a test for the significance of this regressor. So more in general, the test will be a test for the null hypothesis that row 1 is equal to 0 and row 2 is equal to 0 and row tau is equal to 0. The alternative will be that at least one of these guys, one of these regressor will be different from 0. And the LM test is distributed in a large sample. How many degree of freedom do we have? How many restriction are we testing? Exactly tau. 1 equal to 0, row 2 equal to 0, row tau equal to 0. So we are testing joint significance of tau elements. So the test will be distributed like chi-square with tau degree of freedom. Gretel provides an F with tau t minus k degree of freedom. It's just an approximation, but the test should be chi-square tau. And we have finished this, now we can make a break. Is it clear, guys, what you've done? So, basically, testing the absence of correlation in the error term is important. We have two ways to go. We can complement, say, the study of the correlogram, so the Q statistic and the bars and the correlogram, with the Breusch-Godfrey test. Let me say one thing, not always, not all times the two ways give us the same information. We could have some, like one test says something, is not, I mean, we don't have very sharp differences, but there are cases where we could have one suggestion from the test and a different suggestion for the other test. What to do in these cases? I have no answer. We have just to open our mind and to find explanation why it happens. And of course, it depends also very much. What we do depends also on the objectives of the analysis, what we want to do. So it is 4:03. We can take a break and we start again around 4:15. Okay. So I write it on the chat. Okay.